All right, so this time we're taking a look at section 6.4. Which deals with factoring trinomials of the form x squared plus bx plus c, and factoring out the GCF. GCF represents the greatest common factor. Now, in previous sections, we saw how to multiply through something like x plus 4 times x plus 5. And in fact, here we would use the FOIL method, first outside, inside, last. First product, x times x, will be x squared. Outside product, x times 5 gives you 5x. Inside product, 4 times x, 4x. Last product, 4 times 5 gives you 20. And so if you combine your like terms, you got your x squared, you got a 5x plus 4x gives you a 9x, and then you have your 20 as your constant term. Now, a couple of things I want to make note of here. First off, what we have here is a trinomial of the form x squared plus bx plus c. So coefficient of x squared for these types of polynomials, or these trinomials in this section, the coefficient is going to be 1 for x squared. So another thing that I'd like to point out is that the 4 times 5 that you get here is your 20, but the 4 plus 5 ends up being your x coefficient. So when we go to factor, we're not going to start with something like this and end up here. No. We're going to start with something like this and end up here. So essentially going backwards from the multiplying this thing through. So let's take a look at following example. Let's say that we want to factor x squared plus 11x plus 24. So we're wanting to represent this as a product of two binomials. And so we start thinking about how we would do just that. Well, we're going to have some way that we generate the x squared. And the way we do that is we put an x here and an x here. It's that first product in the FOIL method that's going to give us this x squared. But then we need to come up with two numbers, one that goes here and one that goes there. Those two numbers would form your last product, which gives you this constant of 24. So these two numbers have to multiply together to give 24. But as we saw in the previous situation here, if you take a look at the coefficient of x, that was the sum of these two numbers. Here, that sum needs to be 11. So when you put it all together, the numbers that go here and here have to multiply together to give 24, but they also have to add together to give a positive 11. So if we were to use 8 and 3, 8 times 3 is 24, 8 plus 3 is 11. And so you'd have the 8 and the 3 here. X plus 8 times x plus 3 would be your factorization. Let's take a look at this one. You have x squared minus 16x plus 64. And so what we're going to do here is, once again, set up our two binomial factors. And we have this x squared that gets generated by our first product in the FOIL method. So x times x gives us the x squared. But then we're going to have to put two numbers here, one that goes here and one that goes there. Those two numbers have to multiply together to give 64, but they're going to have to add together to give a negative 16. And so if you think about what those numbers are, Negative 8 and negative 8 multiplied together will give you positive 64. But if you take negative 8 plus negative 8, you do get negative 16. So factorization here, we have x minus 8 times x minus 8. Now, whenever you have this form like an x squared plus bx plus c, which we certainly have here, and we also have here, if your constant is positive, then you know that both signs that go here are going to be the same. Could be two positives, could be two negatives, but you know that the signs that go here and the signs that go here are going to be the same. And if that constant is positive, if you want to figure out what sign it is, take a look at the sign that's associated with your b. So in this case we had a positive 11, this was positive as well. Both of these signs were positive. X squared minus 16x plus 64. Okay, the 64 is positive. We know both of these signs have to be the same. This tells us they both have to be negative. And so x minus 8 times x minus 8 happen to work here. And that's kind of a nice thing to keep in mind when you're doing these factorizations. Now, let's take a look at another example. In fact, we're going to take a look at quite a few examples. So in this case, maybe we want to factor x squared minus 3x minus 18. Now, this example differs from the previous ones because the constant term in the first two examples was positive. Here the constant term is negative. Now we're still going to be generating the x squared by x times x. But with this term, this negative 18 being negative, what that's going to tell us is that we're going to have one of each sign here and here. So one of the signs that we're going to have is positive, the other one is going to be negative. The reason for that is the numbers that go here and here have to multiply together to give negative 18. Only way that's going to happen is if they have opposite signs. So not only do these two numbers have to multiply together to give negative 18, they also have to add together to give us negative 3. So if we take negative 6 and positive 3, negative 6 times 3 is negative 18, and negative 6 plus 3 is negative 3. So we know we have the right factorization. X minus 6 times x plus 3. X minus 6 times x plus 3. Now let's suppose that we want to factor the following. Maybe we have a squared plus 6ab plus 8b squared. Well, this one looks a little weirder because you have two variables showing up. But we're still going to try to break this up into a product of two binomials. And so we start thinking about how exactly is it that we would generate this a squared. Well, in order to generate the a squared, we would use the first product in the FOIL method. A times a would give us that a squared. And then we start thinking about, well, what about the 8b squared? Well, we can start this out kind of simple. We know that we're going to have a b squared that's generated by this term and that term and that term. In fact, we're going to need an 8b squared, but let's just focus in on the b squared for a moment. So if we put a b here and a b here, that so far will give us b squared. But then we have to think about coming up with two numbers that multiply together to give 8 and that add together to give 6. So if we go with 2 and 4, then we can put a 2 with a b here, put a 4 with a b there. We'll have positives associated with both of these factors because this is positive and this is positive. And then if you think about multiplying this back through just to check your work, a times a, first product gives you a squared. Outside product would give you a 4ab. Inside product would give you a 2ab, and you add those together, look what you get, 6ab. And then if you take your last product, 2b times 4b gives you an 8b squared. So turns out that this is the correct factorization. Works just fine. Now it could be that you have a polynomial that can't be factored. And if you have a polynomial that can't be factored, it's what's referred to as a prime polynomial. And so I'd like to give you an example, definition and then an example. So for these prime polynomials, we're assuming that we're sticking with just real numbers. We're not trying to factor over the complex numbers, just the reals. And so there are some cases in which you might have a quadratic factor, and there's just no way that you're going to be able to factor that over the real numbers. Good example of that would be polynomial x squared plus 1. Can't factor that over the real numbers. But let's take a look at another example. So if we were to take a look at x squared plus 2x plus 4, you could think about, well, can we come up with two numbers that multiply together to give 4 and add together to give 2, using that strategy. And you might bang your head against the wall for a little bit and think, oh gosh, I can't seem to get this. Well, it could be that the polynomial is prime. And so one way to determine whether or not the polynomial is prime is to take a look at the expression b squared minus 4ac. Now this expression is going to come up a little bit later in chapter 7 when we start taking a look at what's called the quadratic formula. But for right now, let's just focus in on b squared minus 4ac. Now in this case, b is 2, a is 1, and c is 4. So if I take a look at b squared minus 4ac, that's going to give me 2 squared minus 4 times 1 times 4. That gives me a 4 minus 16, which is negative 12, which is less than 0. And it's that less than 0 part that's the key. If I have a prime polynomial, then when I take b squared minus 4ac, I'm going to get something that's negative. I'm not going to be able to factor over the real numbers, guaranteed, if that's the case. Now, if b squared minus 4ac is equal to 0, or if it's positive, then technically you can factor it, but some are going to be a heck of a lot easier than others. So just keep that in mind. Alright. So now let's take a look at factoring out the greatest common factor. Or factoring out the GCF. And so in this example, actually take a look at two different exercises. Let's take a look at 10x squared minus 15x. And then in part B, we'll take a look at 8x cubed plus 20x squared. Now, When we're going to figure out the greatest common factor, what we're going to try to do is come up with a monomial. And we want to make sure that the coefficient is the largest number that we can factor out of each one of the terms here. So 10 and negative 15. Basically what you're looking at is the fact that 5 is the largest number that's going to divide evenly into both. So 5 is going to be the coefficient of that monomial that we factor out. But we also have to look at one other thing. And that is, what is the highest power of x that we can factor out of both terms? So it's not only the case that we can factor a 5 out of each of these terms. When you have an x and an x squared, you can also factor an x out of each. And so if I go to factor out 5x from each of these terms, I start thinking about, well, what would the other factor be? And so if you have 5x factored out of the first term, think about what would happen. Think about what you have to multiply by 5x to get 10x squared. So 5x times what is equal to 10x squared? Now another way to look at that is to say, what is 10x squared divided by 5x? So if I take 10x squared divided by 5x, 10 over 5 gives us 2. X squared over x gives us x. Is 5x times 2x same thing as 10x squared? You bet. And then to get the other piece of this factor, I would say 5x times what gives me negative 15x. Or I could also ask, what is negative 15x divided by 5x? Now if I take negative 15 divided by 5 gives me negative 3. X divided by x gives me 1. So negative 3 would be that other term in that second factor. So here we factored out the 5x from each of the two original terms. 2x minus 3 was the other factor. And it's not going to get any better than that for the factorization. Now we can do something similar for part B. So for part B, we have 8x to the third plus 20x squared. And so once again, to factor out that greatest common factor, we want to factor out a monomial. Coefficient, we want to take as the highest number that can divide evenly into both of these terms. So it looks like 4 is going to be that number. But we're also going to want to take out the highest power of x that's common to both terms, and that's x to the second power. So we got the 4, and we got the x to the second power. That's going to be our greatest common factor. And then we have to ask ourselves, well, what is that other factor going to be? So you would ask the question, 4x squared times what is 8x to the third? Or think of it as the division, 8x to the third divided by 4x squared. 8 over 4 is going to give you 2. X to the third over x squared gives you x. So that works pretty well. And then we can ask the question, what's the other term going to be in that second factor? So in other words, what happens if you factor a 4x squared out of the 20x squared? Well, we ask the question, 4x squared times what is 20x squared? Or we could ask the question, what is 20x squared divided by 4x squared? 20 over 4 gives us 5. X squared over x squared gives us 1. So it looks like 5 is that second term in that last factor. So 4x squared times 2x plus 5 is going to be our factorization when we take the GCF out of both of these original terms. But let's take a look at another example. So let's suppose that here what we want to do is factor 18x to the fourth minus 30x squared. Okay, so 18x to the fourth minus 30x squared. What we're going to do is figure out what's the largest number we can divide evenly into the 18 and the negative 30. And so we get 6 from that. What's the highest power of x that's common to both of these? X squared. So 6x squared is going to be our greatest common factor here. So we ask the question, what times 6x squared is 18x to the fourth? And we can answer that question if we take 18x to the fourth divided by 6x squared. The 18 over 6 gives us 3. X to the fourth over x squared gives us x squared. Well, there's one other piece to this factor that needs to be put up. And so we ask the question, what happens when we factor 6x squared out of negative 30x squared? Or 6x squared times what is negative 30x squared? Now you could look at this perhaps and say, well, that's just negative 5. Or you could say, let's take a look at negative 30x squared over 6x squared. Negative 30 over 6 gives us negative 5. X squared over x squared gives us 1. Negative 5 times 1 is negative 5. So there's our factorization. Now, technically we could factor the 3x squared minus 5, but the factorization is a little ugly, so we're not going to worry about doing that. But we are going to take a look at another example. Now in this example, we have 14p to the fourth times t plus 21p squared t squared minus 70 pt. So this one's a little bit more complicated. But we can still factor out the GCF. If we take a look at the three coefficients that show up, the 14, the 21, and the negative 70, what we notice is that we can divide each of those evenly by 7. And so the coefficient of the monomial that is our greatest common factor is 7. But then we also take a look at the powers of p and t that we have here. Take a look at the powers of p for a moment. P to the fourth, p to the second, p to the first. So the largest power of p that we can take out of each one of these terms is p to the first. So we'll write us p next to our 7. And then we take a look at the powers of t. We have t, t to the second, and t. Well, t to the first power is the largest power of t that we can take out of each of these terms. So we'll put it together with the 7 and the p we had before. So it turns out that 7pt is the greatest common factor among these three terms in this original polynomial. So we can ask the question, well, what goes into this other factor? And so you could say, well, what do we have to multiply by 7pt to get 14p to the fourth t? Well, we know that 7 times 2 is 14. We also know that p times p to the third is p to the fourth. And we know that t times 1 is t, so we don't have to write that extra factor of 1. But you could also think of it as 14p to the fourth t over 7pt. The 14 over 7 gives us the 2. P to the fourth over p gives us p to the third. T over t gives us 1. So that's another way to figure it out. We could then say, well, what do we have to multiply by 7pt to get 21p squared t squared? Well, we know 7 times 3 gives us 21. We know p times p gives us p squared. And we know t times t gives us t squared. So 7pt times 3pt would give us the 21p squared t squared. But you could also do the same thing we've been doing. Take a look at the 21p squared t squared. Divide it by 7pt. The 21 over 7 gives us 3. P to the second over p gives us p. And t squared over t gives us t. And then finally we can ask the question, well, what do we have to multiply by 7 pt to get negative 70 pt? Well, we know that 7 times negative 10 is negative 70. We also know p times 1 is p, t times 1 is t, so negative 10 is going to be that last term in that other factor. But you can also figure it out this way. Put a negative 70 pt over 7 pt. Negative 70 over 7 gives you a negative 10. P over p gives you 1. T over t gives you 1. But this is our factorization. This is just here to try to help us get that factorization. Well, once we have that factorization, we can always erase it and have our final answer right there. Now, we've looked at some examples in which we factored polynomials of the form x squared plus bx plus c. We've looked at some examples in which we factor out the GCF. What happens if we put this stuff together? Well, this example is going to address at least some of that. So we'll have 3x to the third plus a 21x squared plus 36x. We're asked to factor that polynomial. Now I notice that this does not have the form of an x squared plus bx plus c. But I do also notice that every single one of these coefficients is divisible by 3. And I also notice that every single one of these factors has x at least raised to the first power. So I can start thinking about taking out the greatest common factor. Once again, each of the coefficients is divisible by 3, and x to the first, at least, shows up in each one of these terms. So my greatest common factor is going to be 3x. And then I ask the question, what times 3x is 3x to the third? And the answer to that is x squared. What times 3x is 21x squared? The answer to that, 7x. What times 3x is 36x? The answer to that is 12. And of course, if you really want to, if you want to go back to what we've looked at in a lot of these other examples, if you take a look at the 3x to the third over 3x, 3 over 3 gives you 1, x cubed over x gives you x squared. If you take a look at 21x squared over 3x, 21 over 3 gives you 7, x squared over x gives you x. There's your 7x. Take your 36x over 3x, 36 over 3 gives you 12, x over x gives you 1, 36 over 3 gives you the 12. So 3x times x squared plus 7x plus 12 is what we have so far. Now I say so far because we can factor this part as well. X squared plus 7x plus 12, it's a pretty nice trinomial. Certainly has the form x squared plus bx plus c. And so let's try to factor that into a product of binomials. Now the x squared is going to be generated by x times x. But then we're going to need to come up with two numbers. One goes here and one goes there. And those two numbers have to multiply together to give 12 and add together to give 7. We can also tell, because of this constant being positive, and with the coefficient of x being positive, that both numbers are going to end up being positive. But two numbers that multiply together to give 12, add together to give 7. If you're thinking 4 and 3, that's good, because those are the numbers. So this 3x to the third plus 21x squared plus 36x factors into 3x times x plus 4 times x plus 3. That's as good as it gets with the factorization. Now, let's see another example And in this one, we'll factor 5x cubed y squared minus 10x squared y cubed minus 40xy to the fourth. So I want to think about the largest number that I can factor out of 5, negative 10, and negative 40 evenly. I want to be able to divide that number evenly into all three. And so 5 works great for that. So we'll write down the 5. And then take a look at the powers of x. We have x to the third, x to the second, x to the first. There's at least an x to the first that you can take out of each one of these. So we'll write that x next to the 5. And then we have y to the second, y to the third, and y to the fourth. So you can actually factor a y squared out of each one of these terms as well. So 5xy squared, it turns out, is our greatest common factor here. Now, we also have to figure out what the other factor is going to be. So we start to think about what happens if we factor a 5xy squared out of each one of these terms. So if we take 5xy squared out of this first term, think about what happens when you divide 5x cubed y squared by 5xy squared. 5 over 5 is going to give you 1. X cubed over x gives you x squared. And then y squared over y squared gives you 1. So the only thing we have to multiply by this to get here is x squared. But then what happens if you factor a 5xy squared out of the second term? Well, we know that 5 times a negative 2 gives us negative 10. We know x times x gives us x squared. And we know y squared times y gives us y cubed. But another way to look at it, take negative 10x squared y cubed, divide it by 5xy squared. Negative 10 over 5 gives you the negative 2. X squared over x is x. Y cubed over y squared is y. And then to finish out this factor, we ask, what do we have to multiply by 5xy squared to give a negative 40xy to the fourth? Well, I know that 5 times negative 8 is negative 40. X times 1 is x. And then y squared times y squared is y to the fourth. But another way to think of it is negative 40 xy to the fourth over 5xy squared. Negative 40 over 5 is negative 8. X over x is 1. Y to the fourth over y squared is y squared. So we have our factorization so far, but then we have to ask the question, can we factor this thing a little bit more? The answer is yes. Yes, we can. And so we work to factor this trinomial into a product of two binomials. Now to generate the x squared, we're going to have x times x. But then we're going to have to put two expressions into here and here. Multiply them together, they're supposed to give us a negative 8y squared. Now let's just focus on the y squared part for a moment. So if I put a y here and a y here, I'll get y squared. But I need to generate a negative 8y squared when I multiply this term by this one. So there's still some numbers I'm going to have to associate with the y's. Now, I'm going to need two numbers that multiply together to give negative 8 and then add together to give negative 2. If I choose negative 4 and I choose positive 2, that'll do the trick. Now, when you take x times x, you get the x squared. When you take the negative 4y times 2y, you get the negative 8y squared. But then when you take the outside product here, you'll have a 2xy. Inside product, you have a negative 4xy. Add those together, gives you that middle term that we need. So, as a result, this is our factorization, and we're not going to be able to factor it anymore than what you see here. So we have one more example. We'll have a negative 2r to the fourth plus 18r to the third minus 40r to the second. Now, you may look at these coefficients and think, well, each coefficient is even, so I could factor a 2 out. But I also have an r to the second, r to the third, and r to the fourth. So I can take an r to the second out of each one of these terms as well. So you might be tempted to say, let's factor out a 2r to the second. But notice here that the leading coefficient of this trinomial is negative 2. So what I'm going to do is I'm actually going to factor out a negative 2r to the second from each of these terms. Because if I factor a negative 2r to the second out of each of these terms, in particular, factor a negative 2r to the second out of this leading term, then I'm guaranteed that my leading coefficient in this other factor is going to be 1. Notice, I asked the question, what times negative 2r squared is negative 2r to the fourth? The answer, r squared. We've got a leading coefficient of 1 for that factor that's sitting over here. Of course, you could say we can get the r squared by dividing this term by the negative 2r squared. Negative 2 divided by negative 2 gives us 1. R to the fourth over r squared is r squared. And then we can ask the question, well, what do we have to multiply by negative 2r squared to get 18r to the third? The answer, negative 9r. You could take 18 divided by negative 2 gives you negative 9. R to the third over r to the second is r. And then finally, what times negative 2r squared is negative 40r squared? And the answer, 20. You could take negative 40 divided by negative 2, gives you 20. R squared over r squared gives you 1. And so this factor we have here, r squared minus 9r plus 20, goes together with this negative 2r squared. But then we have to ask the question, can we factor this thing a little more? And the answer is yes. Yes, we can. Notice that we have the r squared coefficient is 1. Constant here is positive 20, and the coefficient of r here is negative 9. Now that combination of signs, positive 20 tells us that when we go to factor this thing into a product of binomials, that I know the signs that I see here are going to be the same, and because this is negative, I know they're both going to be negative. Now the r squared is going to be generated by r times r, and as I just mentioned, we know both of these signs here are going to be negative. But we got to come up with two numbers that multiply together to give 20 and that add together to give negative 9. So if you have negative 4 and you have negative 5, those two numbers do multiply together to give 20, and then they add together to give negative 9. So negative 2r squared times r minus 4 times r minus 5 is our factorization. And with that, section 6.4 is finished. So our recommended exercises. One, 5, 9, 15, 21, 27, 31, 39, 45, 51, and 59.